Okay, so welcome to this next video in the playlist on lipid metabolism. In this video, what we want to talk about is the lipoproteins and their involvement in the transportation of lipid molecules around the bloodstream. Okay, so this video is going to be on the different types of lipoproteins and the role that they play in the homeostasis of blood lipid level, basically. Okay, right, so what we're going to begin with is just discussing the different types of lipids, basically, because really an understanding of the different types of lipids is foundational to understanding lipoproteins. Okay, so we're going to begin by looking at the different types of lipids, then we're going to talk about lipoproteins, we'll talk about all the different apolipoproteins, and then what we'll do is we'll discuss the physiology, okay, so what the different lipoproteins are involved in doing and how this is going to keep a constant supply of lipids to certain tissues which like to use lipids, such as the heart and the skeletal muscle. Okay, right, so let's begin then by discussing the different types of lipid molecules that we're going to meet in our later discussions. Okay, so basically, a lipid is the more correct name for a fat molecule, okay? And basically what all of these molecules have in common is that they have very hydrophobic structures. Okay, now hydrophobic means that it doesn't really like water. Okay, now basically what we're going to see is that the chemical structures of these lipid molecules are all going to be very, very neutral, so there's not going to be that much uneven distribution of charge. Everything's going to be neutrally charged, and that means that these molecules can't really interact very well with water, which is a highly polar structure, okay, because oxygen has a much greater electronegativity than hydrogen. Now, electronegativity just refers to how good the nucleus of an atom is at pulling electrons towards it. Okay, so basically each of these covalent bonds between the oxygen atom and a hydrogen atom, those contain 2 electrons. 1 electron from the oxygen and 1 electron from the hydrogen. Now, basically what we want to know is, are these electrons sitting right in the middle, or are they sitting off to one side, basically? And the answer is that they're sitting off to one side. Now, the reason for that is that the nucleus of the oxygen atom pulls on those 2 electrons more than the nucleus of the hydrogen atom. Okay, so the fancy word for how strong the attraction that the electrons will feel towards a nucleus is electronegativity. We say that oxygen has a greater electronegativity than hydrogen, which basically just means the oxygen nucleus pulls on electrons more than the hydrogen nucleus. Okay, so basically this results in the electrons in these 2 bonds here being closer to the oxygen atom than they are to the hydrogen atoms. So that results in the oxygen atom gaining a partial negative charge and the hydrogen atoms gaining a partial positive charge. And this is what is meant by people saying that water has a very polar structure. Basically, because of this uneven distribution of charge, you have a negative side over here and a positive side over here. So basically you have 2 poles of the molecule, and you would call it a polar molecule. Now, this polar structure means that water molecules can interact with each other absolutely fantastically. So if I bring in another water molecule here, basically this oxygen will also have a partial negative charge, and these hydrogens will also have a partial positive charge. Moreover, the oxygen atom has 2 lone pairs of electrons, which are at the centers of negative charge. So the partially positively charged hydrogen can form a very nice electrostatic interaction with this lone pair of electrons here, and this sort of intermolecular bonding is called hydrogen bonding. Okay, and this is a very strong form of intermolecular bonding. Okay, now, basically, if you ram a water molecule up against one of these lipid molecules, which is going to be extremely hydrophobic, okay, so it's a neutral molecule that doesn't have any uneven distribution of charge, then the bond that you get, the intermolecular bonding that you get, is very, very weak. Okay, so water would much rather form intermolecular bonds with other water molecules. Okay, so what tends to happen is that all the water molecules remain close to one another, and that results in all the hydrophobic molecules also getting aggregated together. And this is why if you have a glass of water and you pour, let's say, some vegetable oil into it, what will happen is the oil will split from the water because all the hydrophobic molecules are having to go near one another, and the water molecules are all wanting to be near one another. And basically you should think of it more that the water molecules want to be near one another, and basically all of the lipid molecules just end up pushed to one side and they all end up aggregated together. It's not that they want to be close to each other, it's just that they can't interact with the water basically better than the water can interact with itself. Okay, right, so let's now discuss the different types of lipids then. So the first major type we're going to discuss are the triglycerides. Okay, so triglycerides have many other names, so they're also called neutral fat molecules. Okay, because they are really, really neutral. They are incredibly hydrophobic. We're going to see a lot of examples of lipids. Some of them are more neutral and more hydrophobic than others. Other fat molecules that we're going to see, they will actually have a little polar head which can interact nicely with water. Triglycerides have no such polar head, they are just completely neutral. So triglycerides are often called neutral fat molecules. Another sort of expanded name for triglycerides is to call them triacyl glycerols. And for short, triacyl glycerols can be abbreviated to TAGs, tags. T for tri, A for acyls, and G for glycerols. Okay, right, so let me show you a little cartoon of the structure of a triacyl glycerol. So basically, this is what I'll show you for what a triacyl glycerol looks like. So, the backbone for a triacyl glycerol molecule is basically a glycerol molecule, okay? And this vertical line that I'm now colouring in green here, this is going to represent our glycerol molecule. Now, glycerol is the old biochemist name for this molecule. The sort of organic chemist name, which is a better name for glycerol, is propane 1,2,3-triol. And although propane 1,2,3-triol is a bit of a mouthful, it's a useful name because it tells you exactly what the structure of this molecule is. It tells us that we're dealing with a 3-carbon molecule, that's the propane, and then we have alcohol groups coming off the first, the second, and the third carbons of that glycerol molecule to overall create as a 3-carbon molecule with overall 3 alcohol groups, 1 off each of the carbons. Okay, and the rest of the bonds that each of the carbons has are to hydrogen atoms. Okay, then coming off the glycerol molecule, what we have are fatty acids, okay, and once again, fatty acids is the old biochemist name for something that is more correctly now called long-chain carboxylic acids. Okay, so fatty acids is what a biochemist would call them. An organic chemist would call these long-chain carboxylic acids. And again, that's a useful name because it tells us exactly what we're dealing with here. It tells us that we are dealing with carboxylic acid molecules which have a really, really long tail. So let me show you this structure. Okay, so here is a carboxylic acid head. And basically, I will put an R here to denote an arbitrary tail. But basically, these long-chain carboxylic acids are going to have a really long hydrophobic, which means neutral, tail. Okay, so let me give you an example of a long-chain carboxylic acid. So one of the key examples of a long-chain carboxylic acid is stearic acid, okay, which is a major component of most vegetable oils. Okay. So, the proper name for stearic acid is octadecanoic acid. Hexadecanoic acid is palmitic acid. Okay, so octadecanoic acid. Right. And again, although octadecanoic acid is a little bit of a mouthful, it's a better name because it tells us exactly what we're dealing with here, whereas stearic acid doesn't tell us what we're dealing with. Okay, so octadecanoic acid tells us that we are dealing with an 18-carbon, fully saturated carboxylic acid. So here's the carboxylic acid group, okay, and then we're then going to have 16 methylene groups. Now, I don't want to have to draw 16 methylene groups, so what I'm going to do is a useful trick. I'm going to draw one methylene group, I'm going to put brackets around it like so, and then I'm going to subscript it 16 to mean take this and repeat it 16 times, okay, and then right on the end, what we're then going to end up with is a methyl group right at the end here. Okay, now that is the structure of octadecanoic acid or stearic acid, and it's a sort of archetypal example of a long-chain carboxylic acid. And we can see that it's got a very, very long tail, and basically this is a very, very neutral structure, and the reason it's very, very neutral is that the electronegativity of hydrogen and carbon are roughly the same, which means that all of these bonds are non-polar basically. So the electrons sort of sit in between the two rather than off to one side. Okay, right. So what you're going to do is you're going to take the glycerol molecule, which has these free alcohol groups, one off each of the carbons, and you're going to esterify to each of those alcohol groups a long-chain carboxylic acid. So you're going to bring 3 long-chain carboxylic acids along, and you're going to esterify them onto those free alcohol groups of the glycerol molecule. Okay, so let me just remind you of what an esterification reaction is. So if we draw our arbitrary long-chain carboxylic acid here, basically the carboxylic acid group can react with an alcohol group, and of course the alcohol group is going to be on our glycerol molecule. And basically what can happen is the alcohol group of the carboxylic acid group is going to break off the carboxylic acid group. The hydrogen of the alcohol group is going to break off the alcohol group. You will combine those two things together to make water. Okay, so water is going to be a byproduct of this esterification reaction. And then you're going to bind the carbon of your long-chain carboxylic acid to the oxygen of your alcohol. Okay, and the link that you form there is going to be called an ester link. Okay, so basically this is what you're going to do. You're going to take 3 long-chain carboxylic acids, you're going to esterify them to the free alcohol groups of the glycerol molecule, and this is why it's called a triacyl glycerol, because we've got 3 acyl groups coming off a glycerol molecule. So let me just remind you of what an acyl group is, just in case you're not totally familiar with that term. So basically, when you actually perform this esterification reaction, you do not add the entire carboxylic acid group on. You lose this alcohol group here. So the bit that you're actually going to add on to the alcohol group is this portion here, which I'm now highlighting in green. So it's the carboxylic acid molecule without the alcohol group. This group is called an acyl group. So it's called the acyl group of the carboxylic acid. So that's why it's called a triacyl glycerol, because you've got 3 acyl groups, these 3 orange dangly bits here. Those are attached onto the glycerol molecule, so this is a triacyl glycerol. Okay, right. So that's triacyl glycerols then covered. What we now want to move on to is the next sort of lipid molecule that we're going to discuss a lot in this video. Okay, so the next type of lipid molecule I want to discuss is what's known as a phosphoglycerolipid. Okay, now basically phosphoglycerolipids are all examples of a broader category of molecules which are known as phospholipids. So the set of phosphoglycerolipids is contained within the set of phospholipids. That's just a little bit of maths notation to denote that all of the phosphoglycerolipids are basically phospholipids. Okay, right. Excuse me. So, basically the phosphoglycerolipids are, when people generally think of phospholipids, they generally think of a phosphoglycerolipid, okay, but the set of phospholipids is actually broader than just the phosphoglycerolipids. There are molecules that are considered phospholipids that are not phosphoglycerolipids. Okay, so all you have to have in order to be considered a phospholipid is you need to have a fatty acid within your structure. Okay, so a long chain carboxylic acid such as stearic acid that we've just looked at, and you also need to have a phosphate group within your structure. So it's not a hugely vigorous criterions. There are other molecules other than phosphoglycerolipids which satisfy these criteria and therefore will be considered phospholipids, and we'll see examples of those later. But for now, what we want to look at is the structure of phosphoglycerolipids. So basically, once again, they are based on a glycerol molecule. So as their backbone structure, you have a glycerol molecule, which we'll show in green here. Okay, and then coming off the glycerol molecule, you have two long-chain carboxylic acids, which we'll show in orange again. So we have a long-chain carboxylic acid is sterified to the alcohol group of the first carbon of the glycerol molecule, and then we have another long-chain carboxylic acid molecule is sterified to the second alcohol group of the glycerol molecule. That leaves the alcohol group that comes off the third carbon of the glycerol molecule free. And basically what we are now going to do is we're going to attach a phosphate group onto this. Okay, so all of these phosphoglycerolipids, I should have said this earlier actually, all of these phosphoglycerolipids are going to be based on a structure called phosphatidic acid. Okay, so what we're discussing at the moment is actually the structure of phosphatidic acid. So all of the phosphoglycerolipids are just going to be modified versions of phosphatidic acid. So I want to show you the structure of phosphatidic acid. And basically what you do is you take a glycerol molecule like this, you bind these two long-chain carboxylic acids to the glycerol molecule, and you then bind off the third carbon of the glycerol molecule's alcohol group, a phosphate group. Okay, now I want to discuss how we are actually going to link this phosphate group onto the alcohol group of the third carbon of the glycerol molecule. So let me show you the structure of a phosphate group then. Okay, so a phosphate group has a phosphorus atom at the center. Then it has an oxygen double bound to the phosphorus atom. And then off the phosphorus atom you also have two alcohol groups like so. You then also have a single bond to an oxygen atom. And this oxygen atom then needs another electron to take its outer shell electron number up to 8. So it acquires another electron via ionic means. And that means that it gains a negative charge here. So this is the structure of an inorganic phosphate group. And basically, inorganic phosphate groups can react with alcohol groups in much the same way as carboxylic acids can. Okay, so if we have the alcohol group of the third carbon of the glycerol molecule shown here, then basically, if we look at this structure within the phosphate group in a bit more detail here, so if we look at this thing that I'm circling in purple here, okay, look at what this looks like. If I turned that phosphorus atom into a carbon atom, okay, ignore the fact that it's got 5 bonds, which is obviously absurd for carbon, okay, just look at the portion that I've circled in purple. If that was a carbon atom, this would look exactly like a carboxylic acid group, okay. So basically, this portion of the phosphate group that resembles a carboxylic acid group can react with alcohol groups in much the same way as a real carboxylic acid group can react with alcohol groups. So let me show this. So basically, you can break this alcohol group off the phosphate group. You can break this hydrogen off the alcohol group. you can combine those two together to make water, and you can then bind the oxygen atom to the phosphorus atom just like you would the oxygen atom to the carbon atom when we were doing an ester link. Okay, so it's completely analogous to an ester esterification reaction. Now, it's not called an ester link anymore. Instead, it's called a phosphoester link. Okay, so this sort of a link between a phosphate group and an alcohol group is called a phosphoester link, and I'm sorry it doesn't show up particularly well there. Okay, right, I'll just add in the link as well. Right, so this is what we're going to do. We're going to take an inorganic phosphate group, like so, and we're going to esterify it via this phosphoester link onto the third alcohol group of the glycerol molecule. Now, this structure we have here is what's known as a phosphatidic acid molecule. Okay, now, basically, there was something that I should have told you or emphasized more when we were discussing triacyl glycerols, which is now going to apply to phosphatidic acid just as well. Okay, so I'm just going to go back to triacyl glycerols for a moment. Basically, triacyl glycerols can have many different long-chain carboxylic acids esterified in these three separate positions. So stearic acid was an example, but you can have many different long-chain carboxylic acids esterified onto these three alcohol groups of the glycerol molecule. And the long-chain carboxylic acids that you put in all three positions do not necessarily need to be the same long-chain carboxylic acid. So, for instance, you could have a stearic acid molecule here and then some different long-chain carboxylic acid in this second position. Okay, so there is not just one triacyl glycerol molecule, it's a whole family of related molecules. Just like that scenario with the triacyl glycerols, phosphatidic acid is not just one molecule because it is not set in stone what these long-chain carboxylic acids here are. They can be many different long-chain carboxylic acids, and again, you don't need to have the same long-chain carboxylic acid in this first position as in this second position. So basically, there are many different molecules which would all be considered phosphatidic acid. Okay, right. So these phosphoglycerolipids then are going to be based on the structure of phosphatidic acid. Okay, so what we're now going to do is take the phosphatidic acid and we're going to add an extra group onto that. But before we just discuss that, I'd like to explain why this is called phosphatidic acid. Okay, so basically, this is called phosphatidic acid because this alcohol group that you have here of the phosphate group that is attached onto the third carbon's alcohol group of the glycerol molecule, this can donate away its proton into the solution. Okay, and that's the very definition of an acid molecule. An acid molecule is a molecule which can donate a proton away into the solution. Okay, now when that proton leaves that alcohol group, the oxygen of this alcohol group will be left with a negative charge. Okay, and the whole molecule that you have left is now called something different. Okay, it's called a phosphatidate molecule. Okay, so that's the strict difference between phosphatidic acid and phosphatidate. Phosphatidic acid is the protonated form, and phosphatidate is the non-protonated form, the unprotonated form. Okay, so strictly speaking, this is what we would call the conjugate base of phosphatidic acid. Okay, now what that means is when you take any acid molecule, and this doesn't just apply to phosphatidic acid, it applies to any old acid molecule. When it gives up its proton, the molecule that you have left will have a negative charge. For instance, the phosphatidic acid had a negative charge on this oxygen here after the proton had left. Okay, that molecule is no longer an acid anymore. It can't donate away any more protons. Instead, it has actually become a base because instead it can collect protons from the solution and add them onto itself. So, it's basically called the conjugate base of the acid. Okay, however, having told you about the strict difference between phosphatidic acid and phosphatidate molecules. I will now tell you that people will use these two words interchangeably. Okay, so people will often call phosphatidic acid molecules just a phosphatidate molecule. And the reason is that if you actually made a solution of phosphatidic acid molecules, let's imagine you actually tipped in loads of phosphatidic acid molecules, i.e. all the molecules were protonated. The instant you put them into solution, some of them will dissociate, i.e. they'll lose their protons and they will become phosphatidate molecules. So basically, in a solution, you will always have a mixture of phosphatidic acid molecules and phosphatidate molecules. So often people will use the two words interchangeably. Okay, right. So let's now talk about how we can go from a phosphatidic acid molecule to a phosphoglycerolipid. So basically, what you can do is you can add additional groups onto this phosphate group of the phosphatidic acid molecule. Okay, so you can add on extra groups onto the head of the phosphatidic acid molecule. Okay, now how can you do this? Well, basically, even once we've formed this phosphoester link here, if you can see, look at this group here that I'm now circling in blue. This will still be intact. We'll have this phosphorus atom at the center with a double bond to an oxygen and then an alcohol group. Well, basically, we have another one of these carboxylic acid-like groups. So this can interact with another alcohol group, basically. So we can take another alcohol molecule and basically we can form another phosphoester link. We can take the alcohol group of the phosphate group, we can take the hydrogen off the alcohol group, we can combine those two together to make a water molecule, and we can then link this phosphorus atom here to this oxygen atom down here to form another phosphoester link. Okay, and this is how you can attach another group onto the phosphate group of the phosphatidic acid molecule by another phosphoester link, basically. Okay, so let me give you an example of groups that you can attach on there, and this is how we make our phosphoglycerolipids. So basically, a phosphoglycerolipid is one of these molecules here that I've now got. It's a phosphatidic acid molecule with an additional group stuck on the side. You would also consider a phosphatidic acid molecule a phosphoglycerolipid. It's just where you have nothing stuck on, or a proton, if you like, stuck off this oxygen here. Okay, right, so there are many different groups that you can stick on the side here, and they give rise to a vast family of phosphoglycerolipids. The one that is going to be extremely important for us to discuss is a molecule called phosphatidyl choline. Okay, so basically all of these phosphoglycerolipids, which are derivatives of phosphatidic acid, they have this prefix phosphatidyl here, which tells you that you have the entire phosphatidic acid molecule with an extra group stuck on, which is the choline. Okay, so basically phosphatidyl choline, which is often abbreviated to PC, is just going to be one of these phosphatidic acid molecules with a choline group stuck onto that phosphate group. Okay, so let me now show you the structure of a choline molecule. And basically, we know one of the functional groups that it's going to have is going to be an alcohol group. Now, choline is actually the same choline that you have within acetylcholine. In acetylcholine, you have an acetic acid molecule esterified to the choline alcohol, and that's acetylcholine, the famous neurotransmitter. Okay, so a pure choline molecule, however, looks like so. Here's the alcohol group. You then have an ethylene group, which I'll show like so. So this is this 2-carbon structure. And then on the end of the ethylene group, you then have a nitrogen atom, and this nitrogen atom has 3 methyl groups coming off it. 1, 2, 3, like so. Now that leaves this nitrogen overall with 4 bonds. Nitrogen doesn't like having 4 bonds, it likes to have 3 bonds. Okay, so into one of these bonds, the nitrogen will have actually donated both electrons. Now, the normal understanding of a covalent bond is that one electron comes from the nitrogen and one comes from the carbon. Okay, but in this example, the nitrogen has donated both electrons into one of these bonds. 3 of them will be a normal covalent bond, but one of them, let's say it's this one here, will have actually been the case that the nitrogen put in both electrons. Now, when the nitrogen puts in both electrons into a covalent bond, it is as though the nitrogen has lost an electron, because, as I say, the normal understanding of a covalent bond is that one electron belongs to the nitrogen and one belongs to the carbon. So if the nitrogen puts in both, it's like the nitrogen has given one away to the carbon. So that gives this nitrogen a positive charge here. Now you might ask, well, surely the carbon should get a negative charge, okay, because we've given the electron to that carbon. But that carbon, when it came in to bind to the nitrogen, will have originally had a positive charge. So when it received the electron from the nitrogen, it was neutralized, which is why it's still neutral, and it's deferred the positive charge onto the nitrogen effectively. So, the whole choline molecule then does have a positive charge. So what you're going to do is you're going to link this choline molecule onto the phosphate group of a phosphatidic acid molecule via a phosphoester link, and that will create you phosphatidyl choline, okay, often abbreviated as PC. Now there is another name for phosphatidyl choline, which is quite commonly used, and we're going to use it later, which is lecithin, okay, so it would be nice if you could remember that name because it's often used. It's the old name basically for phosphatidyl choline. Okay, right, so I think we'll call it there for this video. In the next video what we'll do is discuss sphingolipids and then cholesterol and cholesterol esters, and then we'll move on to lipoproteins.